All right, folks, we're back. We're going to be talking about a fun section today, which is 12.13 on applications of PCA. And the applications are basically what I think most people's interaction with PCA is all about. So it's not just a theoretical aspect, but using it. And we're going to discuss three applications. The first one is going to be data compression, which is kind of what we've been talking about so far. And then later on, we'll talk about perhaps a lesser known one, which is how use PCA for standardizing your data. So to make it uncorrelated and unit variant. So it's called this is called whitening or sphering, because whitening is kind of think of colors and the variance along each direction kind of representing the amount of contribution of each color. You want all the variants to be the same, and the sphering means you want the decorrelation. So you don't want any of the you don't want these oblong shapes. So it's often known as a whitening transformation or a sphering transformation. We'll see how PCA does that. And then finally, we'll talk about probably the most common application of PCA in my experience, which is actually the data visualization. So projecting the data into the first two, sometimes the first three principal components to get a sense of it. So there's just a kind of a plot that we'll discuss about that. So three applications today. Let's get into it. Okay, so we can illustrate the use of PCA for data compression by considering the offline digits data set. So because each eigenvector of the covariance matrix is a vector in the original d-dimensional space, we can represent the eigenvectors as images of the same size as data points. So this is actually one of the really cool things about PCA, is that the mean and the eigenvectors, they're going to live in the same space as the data. So you can, if you can visualize, the data as pixel images, well, you can do the same thing with the eigenvectors and the mean, and then you can look at it and see, like, does that make sense? And so here we've done that. And as always, it's really good when you're trying out a new algorithm, even as simple as PCA, try it on data where you understand what's going on. Because then you can tell, are you just, have you coded it right? Do you understand how it works? Is it giving you answers you expect? And because, data sets you're going to try to understand, well, by definition, you don't understand how they work. So if you also don't understand whether your tool is working correctly, you're just never going to get anywhere. So make sure whenever you're trying something new, do it on data first that you understand. So here we're going to apply PCA to this data set composed of the digits three people have written. These are long vectors, 10,000 element vectors, something like that, but we've rearranged them into the pixel images that they are. And now look at this. Look what we have. So this is the mean of that data set. And that looks reasonable to us, right? We can look at that. Yeah, that looks like a 3. So I would imagine a data set of 3s. The mean pixel image should look like a 3, which is what we have here. And now let's look at, these are kind of the first 4 principal components. And we have to kind of guess what the color scheme is, but presumably blue is positive and yellow is negative. And let's look at this particular data set, and it looks like it's kind of capturing 3s that are a little bit shifted forward compared to this average one. So like maybe there's a bit more action here and a bit more action towards the back. And because these are unit norm, if you add values somewhere, you have to reduce values somewhere else. So that means that the back end has been kind of cut down a bit, and maybe kind of some of this front action has been cut down a bit. So that represents a particular shape of 3. Here's another one where maybe it's like slightly shifted back. I don't know. Over here, it looks like maybe people do a kind of very thin 3. So we've got very large values on a thin band, and then small values. And also one thing I want to point out, it's not to say that people like do one kind of 3 and this means that they do another kind of 3. It just means that the range of 3s that are encountered are well captured by combining these types of variability. It might turn out that, yeah, there is actually just 4 different 3s that people do. But in reality, it won't be like that. It just means that these directions are useful for describing the range of 3s that people draw. Okay, so the first 5, it's actually 4 eigenvectors, along with the corresponding eigenvalues are shown in 12.3. Right, remember, these eigenvalues are going to be the variances that are captured by each one of these directions. And you can see that, okay, so this one is 3.4 times 10 to the 5, is 1.6 times 10 to the 5. So there's still actually quite a bit of variance being captured relative to this kind of this top direction. The distortion measure J associated with choosing a particular value of m is given by the sum of the eigenvalues from m plus 1 up to d and is plotted for different values of m. Okay, right. So here, let's have a look at this. Okay, so you guys can't quite see this, so let me see if I can zoom. Yeah, okay, just about. Okay, so this is going to be, this is the very first plot. And it's actually okay, we're kind of focusing on it. So on the x-axis, we have component, principal component. On the y-axis, we have the amount of variance that it captures. You can see the first few. In many data sets, you kind of get a picture like this, in my experience. It's not, it's not always quite so sharp as this. And it will always decrease. The decreasing is not, it's just because of PCA. You order the variances in decreasing order. So this curve is always going to go down. The question is how quickly it goes down. And yeah, so for a data set like this, it looks like it actually goes down very reasonably quickly. So with the first 20 data sets, 20 principal components, there isn't really that much variance left. And often we use data like this, but presented in a different way to actually select how many principal components to choose. And the way we do that is, well, we think of what is the total variance. So you guys can see this. So like the total variance, let's say t is going to be equal, the sum on yi, I is equal to 1 to n. And then we plot the cumulative variance. So let's say, I'll just call it c of n. And that's going to be the sum on I is equal to 1 to n of the variances divided by the total variance, right? So it's cumulative variance when n goes to however many components you have will be 1. And when n is equal to 1, it'll just be the first principal component scaled by the total variance. So if we were to actually plot this, it will have be a monotonically increasing, and it'll often look like something like that. And we'll actually, and the axes will be going from 0 all the way to 1. And what people typically do is they'll say, look, I'm going to pick enough principal components, like maybe on this many, so that I've captured, 90% of the variance, right? So he said if I capture so and so many components, I will have captured some amount of the variance. Okay, I want, and the number is typically arbitrary, but it's some high number. They'll say, okay, I picked the first 3 components because they capture, 80% of the variance. And it's actually kind of useful because, when you're doing data visualization, right? We'll talk about that at the end. You pick the first 2 principal components. There's a lot of action there, but how much are you missing? And this tells you that. It tells you, okay, if I pick the first 2 components, maybe I'm getting 67% of the variance of the data. Sometimes you actually get much less. So sometimes you actually get 10%. So you're like, well, this picture that I'm looking at, maybe it's not telling me everything. But if you're getting about 6, I don't know. I don't want to make up a number. But if you're getting some high percent of the variance, you're like, okay, as far as this method goes, we're capturing most of the action is happening along these directions. And we're probably seeing, a lot of what's going on. Okay, so that's kind of the variance. In the next plot, so let's zoom out. So this is actually this distortion measure. So the amount of energy left, and you can actually, if you rescale this. So this is, this distortion is, the amount left if you take more and more components. Notice that it goes down to 0. So now we can compare it to our cumulative. It's just 1 minus the cumulative if we scale it properly. So if we say, the cumulative n, which you guys can see, is 1 minus this distortion measure over the total. So these two are kind of quite related. So, it'll just be that cumulative variance explained will just be the flip of this, it'll just look like this, and scaled by the total variance. Again, this just tells you again, after you can kind of view it the same way. I mean, again, these numbers, it probably helps to normalize by the total variance. Otherwise, like, what does this number mean? But you can say, okay, well, if I pick the first 20 components, I have about 10% of the variance left. So I'm just going to work with that, with that smaller data set of data for visualization, for compression, etc. Okay, so let's get back to where we were. I'm going to scroll up. Okay. Distortion measure, and it's plotted for different. Okay. If we substitute 12.12 and 12.13, we can write the PCA approximation of the data vector as the form. So notice what we have here. So we've got our data set, and the first m components we're just reconstructing, in the basis, and with data-specific terms. So sorry, the first M, capital M. But notice that the remaining components we're just setting to their mean value, right? This is where the data compression comes in. And the cool thing is you can actually just rearrange this and you say that I'm going to approximate each data point as the global mean plus a deviation from the mean, an M component deviation from the mean. And the question is, how do you pick those directions? Well, it's along the principal component. So this is kind of another way of viewing, I think kind of very intuitive way of viewing the data compression aspect, right? Like if you were to, if you wanted to summarize your whole data set by one point, it would be the mean, you know, if you use the squared error criterion. If you want to use, you know, more points, well, the question is how to pick them, and the principal components allow you to pick them. So you pick coefficients relative to the mean along the principal directions. So kind of a very nice way of understanding what PCA is doing. Okay, where we have made use of the relations, so and so. Okay, this represents a compression of the data set because for each data point, we have replaced a d-dimensional vector n with m-dimensional vector having these components, the deviations from the mean projected onto that component. The smaller m, the greater the degree of compression. Examples of PCA reconstruction of data points for the digits data set are shown in 12.5. So let's look at 12.5. So here is this original data set, and now we're going to reconstruct it, right? So this is with just one component, and this looks a lot like it looks a lot like the mean to me. So I think he might mean if we just use the mean, and now if we use the mean and like the first 10 components, and you can see that, you know, once we're using 250 components, we've actually gotten, you know, it looks a lot. There's still some speckly bits around, but it looks a lot like the original data. So we don't need, and M is 250 sounds like a lot, but this data is like, I think, yeah, 784 dimensions. So already about, you know, a third of the way of those, if we pick our directions properly, we're a third of the way through, we've basically already captured the shape. And we can look at that here, right? So already by about, you know, 250, there basically isn't any variance left. Okay, so this is kind of a way of, again, visualizing how your compression is doing. Try to reconstruct your data. All right. So that was the first application. Another application, now we're going to talk about the whitening and kind of standardizing of data, right? Okay, so another application of principal components analysis is data pre-processing. So the goal is, let's highlight some of that. The goal is not dimensionality reduction, but rather the transformation of a data set in order to standardize certain properties, right? So that's pretty cool. Why would we want to do that? This can be important in allowing subsequent pattern recognition algorithms to be applied successfully to data sets. So he's going to give us an example. It's done when the original variables are measured in various different units or have significantly different variability. For instance, in the old faithful data set of, I think, the times between small and large eruptions of a geyser in Yellowstone National Park, the time between eruptions is typically an order of magnitude greater than the duration of eruption. I see. Okay, time between eruptions and duration of eruption. So if we, you know, one of them's going to be maybe, I don't know, hours, days, the other one's going to be, you know, in minutes, right? So if we measure both in minutes, you're going to have one variable being very large and the one being tiny, and that's going to cause problems. When we applied k-means algorithm to this data set, we first made a separate linear rescaling of the individual variables such that each variable had zero mean and unit variance. Okay, so this is what we did, standardizing the data set. And the covariance matrix for the standardized data has components this, right? This is the mean subtracted divided by variance. And there's known as the correlation matrix, right? So it's going from -1 to 1. And 1 means they're perfectly correlated. -1 means they're perfectly anti-correlated. 0 means they're uncorrelated. So are perfectly correlated, and if they're uncorrelated, then so and so. Okay, so now it says using PCA, we can make a more substantial normalization of the data to give it zero mean and unit covariance so that different variables become decorrelated. So that's the thing. So if we just standardize, our variables are still going to be possibly correlated. So what does standardizing mean? It just means, so let's say we have kind of a data set here. So it means shifting the mean over here, and then shrinking the two dimensions so that they have unit variance. So like maybe it would kind of get, so this dimension is going to get squished by some amount. Maybe it's already, let's just say this was already unit variance, and then maybe we'll squish this one a little bit more. So like that's what these scalings are doing, so that we get the variance along both dimensions. Let me redraw that. So this would be the variance along one dimension, the variance along the other dimension, and you just squish the data to make it to make them have unit variance. But you don't necessarily get rid of this trend, right? The data will still remain potentially correlated. So PCA is going to actually remove the variable, allow you to remove the variances, so standardize the variances, so make them unit variance, but also remove the correlations. So you essentially transform this data set, it will become sphered. So this will be unit variance in these directions. Okay, so that's kind of what we're talking about here. So using PCA, we can make a more substantial normalization and units. So so let's just highlight this because this is important. I'm going to underline it actually. So that different variables become decorrelated. To do this, we first write the eigenvector equation 12.17 in the form. So this is the covariance, and so this is just saying it's a covariance matrix, and we've just stacked up all of the eigenvalues and eigenvectors. So this is just saying the same thing as, but we're just stacking it up. So this is like, u1 to un, and this is going to be again u1 to un. These are the vectors, and now we have this vector of this diagonal matrix of eigenvalues all the way. So that's just essentially packing the same. We have n different equations, which you can just pack them into one matrix equation. Okay, where L is a d by d diagonal matrix with elements lambda I, and U is a d by d orthogonal matrix with columns given by the eigenvalue. So all we do is, what do we do? So we just take data, we project it onto our direction. So first we mean subtract, then we project it. So let's see what's happening in each one of these stages. So here's our data. So mean subtraction is going to move it over here. Then the second projection step, what's it going to do? It's going to rotate effectively the data. So we're going to project it, onto these coordinates. So the projections onto these coordinates, if now this was, let's say the E1, E2 coordinate, this is U1, U2, well, it's just rotated your data, right? And then finally, this step, it just normalizes data by the variances along the different directions. So notice that this is -1/2, right? This -1/2 is exactly like this. These are standard deviations. Well, that's what that is. It's the square root of the variances, which is standard deviations, and it's -1/2 because we are dividing. Okay, so highlight this, it's -1/2. Okay, so that's all we're doing, right? So this is like a multi-stage process. It looks complicated, but we mean subtract. So mean subtract, decorrelate or rotate, standardize. That's all it is. Boom, boom, boom. We do it. And we get our whiten data. So clearly the set yn has 0 mean because we subtracted the means. And its covariance is given by the identity matrix. So you can actually kind of work it out. And so notice that we've got S in the middle, but if you actually unpack S, then you'll see that it actually has U, L, U transpose. So it's fun to kind of cancel everything out. But you should just be able to see from this multi-stage process that it's going to have unit covariance. Identity covariance, sorry. So this operation is known as whitening or sphering the data. Okay, so let's just highlight these things. And let's have a look. So again, I think you guys can't quite see, so I'm going to zoom in. So here's the original data for this. Notice the two scales, right? This is, I guess, the duration. Presumably, this is the duration of one of the water spouts, and then this is the eruptions, and then this is the time between them, and they're very different scales, right? So, and now you can see, so the original data. The center plot shows the result of standardizing the individual variables to zero mean and unit variance. So this is what you would get by just normal standardization, right? Minus 2 to 2, and now you're over here. But now we want to actually decorrelate. Notice there's still a big correlation. So now we actually want to decorrelate the data. This also shown on the principal axis of the normalized data set, plotted over the range plus minus lambda y over. And this is kind of quite useful, right? Because it kind of tells you, the lambdas tell you, the square roots of the lambdas gives you standard deviations. The plot on the right shows the result of whitening of the data to give it zero mean and unit covariance. Okay, so now this data, when you look at it, there doesn't seem to be any, there shouldn't be any correlations, and I can kind of convince myself that's the case. So that's kind of a nice view of how this whitening works, and you might need it for certainly standardization you have to do most of the time, because algorithms are going to have a very hard time dealing with units that are going to the hundreds in one direction and 2 in the other direction. But sometimes you need to do more, and PCA essentially allows you to do that. Okay, so that's that. Yeah, so it is. We haven't covered LDA so far yet, but let's just point this out as we go, and we'll touch on it again when we go back to chapter 4. Compare PCA with the Fisher linear discriminant, which was discussed in 4.14. Both methods can be viewed as techniques for linear dimensionality reduction, but PCA is unsupervised. So let's highlight that. And depends only on the values x of n. Whereas Fisher linear discriminant also uses class label information. So it's actually a really interesting method, because we don't care what the labels are. We just look at the data itself. Imagine it's unlabeled, like it was for the Geyser data. But yes, so check it out. So this is actually kind of a very, very cool example. So he plotted two things. So the Fisher linear discriminant tries to find directions that split your data, that put the data in the different groups when you project on those directions as far apart as possible. So it's not the same as trying to find a direction that maximizes the variance in the whole data. It's just saying you've got 2 groups or n groups, find directions that best split the data. Okay, so this is actually a very cool, I think very informative example. So here the data is in 2 dimensions belonging to 2 classes shown in red and blue. PCA chooses the direction of maximum variance shown by the magenta curve. So it seems like if we just took away the labels, projected on this direction, well, we'd have like a ton of variance, right? Because that's, the data's lying along this direction. But if you want to split them, actually the direction you want is this one, right? Because if we project onto this axis, then the blue is over here and the red is over here. Whereas if we project it onto this axis, they're actually quite mixed up. So that's kind of the intuition. So maximizing variance is not necessarily always what you want. If you have labeled data, you typically want to split your data, and then the directions are different. So just kind of good to know, good to have that in mind. So that's, and then finally, another common application of principal component is for data visualization. So here, each data point is projected into a 2-dimensional principal subspace, so that a data point x of n is plotted at Cartesian coordinates given by its projections onto the first 2 components, corresponding to the largest and second largest eigenvalues. An example for the oil flow data set is shown in 12.8. So there it is. He's labeled it, but yeah, this is kind of probably the most common application of PCA. It's for data visualization. You find the direction of the most variance and look at your data. And because everything is linear, it actually kind of gives you an undistorted view of your data. You're still missing all the remaining components, so you have to keep that in mind. But there haven't been any kind of crazy transformations of the data set. So it's kind of always good as a first pass exploratory analysis to just look at your high dimensional data with PCA. Good. Okay, so I think with that, that's all I wanted to discuss in this section. Hope you found that useful. As always, just let me know in the comments. And next time we're going to talk about application of PCA for high dimensional data. So how to actually do find these components for high dimensional data sets where some of the operations can be quite costly. So that'll be kind of a short section then. All right, so I hope to see you there. Bye.